Okay, I guess we can get started. Are there any questions before we start? Okay, if not, so there are two objectives today. I want to talk about the so-called split radix FFT. So that's one topic. The second topic that I want to talk about is composite FFT. So that's our agenda for today. And then if there is time, I will talk about the homework for next week and we'll walk through that. Okay, so we looked at Kulitukki FFT and we saw the decimation in time and decimation in frequency. So let's start with split radix FFT. So the basic idea, so okay, what was the main idea in Kulitukki algorithm? So in the decimation in time DIT, we downsample the time to even and odd. And the outputs were in order. In DIF, we explicitly computed the even DFTs using a separate equation and the odd DFTs using another equation, and these were in order. Okay. So in any event, if you look at this DIT and DIF, here we explicitly used k equal to 2r to compute the even DFTs and 2r plus 1 to compute the odd DFTs. So the basic idea of split radix is to basically compute, instead of two equations, compute three equations. Okay, think about that. That's really what we are doing. So the first equation is exactly same as what we computed last time. And so that's the even. And the odd, instead of just computing x 2r plus 1, we are now going to use k equal to 4r plus 1 separately, and then k equal to 4r plus 3 separately, and those two together will describe all the odd DFTs. Okay, so that's what we are going to talk about. So without deriving any further, I think what we had seen last time is x2r was the n by 2 point DFT of xn plus xn plus n by 2. Let me just take a look. I think that was the equation. DIT. Okay, so the DIF, we substituted k is equal to 2r, and then we showed that is equal to n by 2 point DFT of xn plus xn plus n by 2. So you can see that I'm not going to derive that anymore. So we already solved that. So now let's write down what are these two quantities. Okay. So x 4r plus 1 is equal to summed over n equal to 0 to n minus 1. Okay, I should say a little more. Okay, so once we compute x to r, as we write down here, this is computed using 1 n by 2 point DFTs. Okay. Whereas these two are computed using 2 n by 4 point DFTs. Okay, so that's something to keep in mind. So basically the split radix, instead of using 2 n by 2 point DFTs, it uses 1 n by 2 point and 2 n by 4 point. So that's what we are going to talk about. So when we compute these two equations, the length of the DFT will be n by 4. So n equal to 0 to n minus 1 xn e to the power minus j 2 pi over nkn, and then I can write this down as summed over n equal to 0 to n by 4 minus 1 plus n equal to n by 4 to n by 2 minus 1 plus n is equal to n by 2 to 3n by 4 minus 1 plus n is equal to 3n by 4 to n minus 1. Okay, so why is it that we are writing them down in lengths of n by 4? Because we want to compute n by 4 point DFTs. So we divide the length n sequence to 4 parts, each of length n by 4. Okay, so that's the reason. Okay, and then this is xn times e to the power minus j 2 pi over n. Now, so this is really not k. I should be substituting this k as 4r plus 1. So n times 4r plus 1. Okay, 4r plus 1 times n. So that's the first part. This part is xn e to the power minus j, same thing. Okay, 4r plus 1 times n, xn e to the power minus j 2 pi by n, 4r plus 1 times n, xn e to the power minus j 2 pi over n, 4r plus 1 times n. Okay, so that's perfectly fine. And then we are going to do those same substitutions. N minus n by 4 is equal to a dummy index m. And then I can put back m as n. So think about, so this n is equal to m plus n by 4. Okay, so so I can write this as, well, I can, okay, let's just stay as m, it doesn't matter. M equal to 0 to n by 4 minus 1, and this n becomes m plus n by 4. Okay, so this will be same thing, 0 to n by 4 minus 1 and m plus n by 2 and m equal to 0 to n by 4 minus 1 and n plus 3n m plus 3n by 4. Okay, so that's similar manipulation as last time. We are just making all these indices same because we will eventually collect these terms together. So, so let's spend a little time. We'll get back to these indices, but let's spend a little time looking at what these complex exponentials are. So e to the power minus j 2 pi over n times 4r plus 1 times m, this is the second term, multiplied by e to the power minus j twice pi over n times 4r plus 1 times n by 4. Okay, so this term here is equal to this times that. Okay. Any idea what this might be? So n is cancelled out, 2 is cancelled out. So this is complex exponential of an odd pi by 2. E to the power minus j pi times 4r plus 1 times divided by 2. So what do you think? This is like e to the power minus j 3 pi, e to the power minus j pi by 2, e to the power minus j 5 pi by 2, etc. Is that plus j or minus j? Minus j. Okay, good. Very good. So that quantity is equal to minus j. So let's look at, so I'm going to leave it for now as it is. Let's not worry about that. The reason I'm not going to manipulate that now is because that same thing as here. We can take that outside a bracket, so let's leave that. Let's look at the last two here. So what happens when this term is n by 2? So let's look at that complex exponential, e to the power minus j 2 pi by n times 4r plus 1 times n by 2. Okay, so what is that quantity? And then the next one, e to the power minus j 2 pi by n 4r plus 1 times 3n by 4. So that is that term here. Okay, so what exactly are these quantities? So let's take a look. So n is cancelled out, 2 is cancelled out. So this is e to the power minus j and some odd pi, and that's minus 1, right? So that's simply minus 1. If it was even pi, that would be plus 1. What about here? N cancelled out, 2 cancelled out, and this is minus j 3 pi by 2. So this quantity here is e to the power minus j 3 pi by 2, e to the power minus j 7 pi by 2, etc. And this is same thing as 1 at an angle minus 3 pi by 2 is same as 1 at an angle plus pi by 2. And this is same as, well, if I just add 2 pi, 4 pi, so that's going to be just j. So that quantity is equal to j, plus j. Okay, so we spent a little time finding out what those terms are. And then if I come back here, and I can place all these dummy indices back to n. So these are m, I can put them back to n, it doesn't matter. Then it becomes the same index as that n, and we can take them all outside a bracket. Okay, let's try to, okay, let me do this. Let me clear out these terms, and that's minus j, that term removed, minus 1, that term removed, plus j. Okay, so that's what we have now. And then we will so I can write this as equal to summed over n equal to 0 to n by 4 minus 1. Let's group the first and third. One more small mistake. So when I replaced n by m plus n by 4, this would have been m plus n by 4. This is m plus n by 2. And m plus n 3n by 4. So I have already replaced m by n, the index m. So if I collect the first term here and the third term here, so these are the two things without any j, and the second and fourth, this is minus j plus j. So if I take these two terms together, this is a minus quantity. This is a minus quantity. So what do I get? I get xn minus xn plus n by 2. Okay. Okay, so that's so this xn minus x, this is n, dummy m is now back to n, times, then this is the same thing. So we can leave it as that right now. E to the power minus j, actually, okay, let's just leave it like that. Minus j 2 pi by n times e to the power minus j 2 pi by n for r. Okay, so that's those two quantities. What about the next two? So that's n plus n by 4 minus j taken outside the bracket. So that's plus minus j times n equal to 0 to n by 4 minus 1 xn plus n by 4 minus x n plus 3 n by 4 times everything else is same, right? Everything else is same. So so that's the same as this quantity here. Okay, same thing here. Okay, so then we could write this whole thing as summed over n equal to 0 to n by 4 minus 1 xn minus xn plus n by 2 minus j times xn plus n by 4 minus xn plus 3n by 4. Okay, so this whole thing multiplied by e to the power something else is missing here. Something else is missing here, that n that I had, and that is going to be 2 pi over n times n. Is that yeah, so that n has to be there. 4r n plus n. 4r n 4r n and then n. Okay, so e to the power. So let me now write this quantity as w to power n. So this whole thing times that's simply w to power n. Okay, so that's this thing here is w to the power n, and this whole thing times e to the power minus j 2 pi by n. Bring that 4 down, n by 4 Rn. Okay, so it is a little complex, but that's really what it is. So now you will recognize that this is the n by 4 point DFT of whatever is inside that red bracket. That red bracket. That's the complex exponential. So n by 4 point DFT of xn minus xn plus n by 2 minus j times xn plus n by 4 minus xn plus 3n by 4 times w to the power n. Okay, that is the n by 4 point DFT of that whole thing. I think it probably, I don't want to spend 10 more minutes, but what happens if I just change the 1 to a 3? If I just change the 1 to a 3, everything else is same, right? So 4r plus 3, 4r plus 3, 3, 3, 3. And when I evaluate these complex exponentials, let's see. Yeah. So what will happen when I multiply this 4r plus 3? So instead of 1 times n by 4, 1 times n by 2, 1 times 3n by 4, these will become 3 times n by 4, 3 times n by 2. Okay, so let's just for now, let me just write down what I think will be the final result, and we can debate more. We can certainly discuss if that makes sense. So x 4r plus 3 is going to be n by 4 point DFT of xn minus xn plus n by 2. That minus j will become plus j, xn plus n by 4 minus xn plus 3n by 4. Okay, I think it looks like I need another bracket before multiplying w to power n. So w to power n is multiplied with that whole thing. So another bracket times w to the power 3n. Okay. That's what it will be. Eventually, if we go through the same kind of analysis, it will be w to power 3n. So these three equations describe the split radix FFT. Okay, so so what happens if n is equal to 4? N by 4 is what? 1. N by 4 point is 1 point. 1 point DFT. Well, 1 point DFT is the same as itself. Okay, so if we start with 0, 1, 2, 3 time domain samples, then the even DFTs x to r are the 2 point DFTs of the n plus n by 2. N by 2 is 2, 0 plus 2, 1 plus 3, and that's one butterfly, that's x0, x2. Okay, what happens if I just substitute n is equal to, by the way, when cap n is equal to 4, this summing index has only one value, that's 0. 1 minus 1 is 0, 0 to 0 is same as 0. And so if I just substitute n equal to 0, so what do I get? 0 minus 2. 0 minus 2, that's that butterfly here. I'm not writing this as minus 1, but that's minus sign. 0 minus 2, that's 0 minus 2. Minus j times, substitute 0, n is 4 by 4 is 1. 1 minus 3, 1 minus 3. So that's 1 minus 3. Multiply this by minus j and then add to that w to power 0 is 1. There's nothing more to do. W to power 0 is 1. And for x 4r plus 3, this is 1. For x 4r plus 3, that's so this thing is here 0 minus 2, this thing is here 1 minus 3, plus j, that's minus j multiplied by another minus 1 here in the butterfly, that became plus j. N is 0, n takes one value, w to power 0 is 1, so that's same as itself, and that is the 4-point split radix butterfly. And you can see that this probably looks like something else we have seen before. So that's the n equal to 4 point. So what happens to the split radix for n is equal to 8 point? So for the 8-point split radix FFT, the even part is same as before, n plus n by 2, n by 2 is 4, 0 plus 4, 1 plus 5, 2 plus 6, 3 plus 7. Okay, now what are we supposed to place here? What we place here is the 4 point. That's n by 2 point. So use the same split radix FFT. So what should really be placed here? Nothing but this one. So this is the 4-point split radix FFT. So just grab this and paste it here, right? So the only thing here is minus j, everything else looks familiar. Okay, and these are going to be the even DFTs 0, 2, 4, 6, and if you look at the locations of 0, 2, 4, 6, so this becomes even of the even, so this will be 0, 4, 2, 6. Okay. So now let's go back to that equation we had for x 4r plus 1. Okay, that's x 4r plus 1. Okay, so let's take a look what it says. In this case, cap n is 8. 8 by 4 is 2. 2 minus 1 is 1. 2 minus 1 is 1. So that means this n will take two values, 0 and 1. This will take two values, 0 and 1. And this will eventually be a 2-point DFT, n by 4. And this n will take two values, 0 and 1. Okay, so let's start here. So n takes two values, 0 and 1, 0 minus 4, 0 minus 4, and then when n is 1, 1 minus 5. Okay, and then these two here, n is 0, this 8 by 4 is 2, okay, so 2 minus 6, and then when n is 1, 1 plus 2 minus 1 plus 6, 3 minus 7, so 2 minus 6, and 3 minus 7. Okay, and then we multiply minus j to these quantities, these two quantities. So multiply minus j to these two quantities. Nothing is added to those. So they stay the same. Okay, so now what are we going to do? So this is going to be 0 minus 4. I already have that minus j here. So plus 1 minus, excuse me, 2 minus 6. So n is 0, 2 minus 6, 0. Okay, this is 0 minus 4, 0 minus 4, and then 2 minus 6. Okay, so that is that butterfly, that quantity, and this is the other quantity, n equal to 1. And then we are going to multiply this whole thing by w to power n, so that's w to power 0, which is 1, and that's multiplied by w. And then take the 2-point DFT, the butterfly, and that's going to be x 4r plus 1. Okay. The other equation 4r plus 3, everything is same. This is plus j, only difference multiply by w to power 3n. So this is going to be, so we complete that butterfly. Complete that butterfly, multiply by 1, multiplied by w to power 3. So w to power 3n, n is equal to 0, n equal to 1, and then take a 2-point DFT of that, and that's x 4r plus 3 and 4r plus 3, so which are 3 and 7. So that's the complete 8-point split radix FFT. And you can, so if you do a 16-point DFT for the even 8-point samples, grab this and paste that thing there, and that's really what I want you to do. But that's, let me just, it's not really, I grabbed something from the internet, but the minus j's are not shown here, but this is kind of what that will look like. So if you see what I just did, so by the way, the butterflies are shown by this cross rather than the actual full butterfly. And if you look at why they became, why is it that these are written as w squared and w to power 6 instead of w and w cubed? Because w and w cubed with respect to parameter 8 is the same as w squared and w to power 6. W8 to power 1 is same as W16 to the power 2, W8 to the power 3 is same as W16 to the power 6. Okay, that's the reason why those two quantities are 2 and 6. Everything else is same as here. Only thing it is not showing you are these minus j's. So that's not shown here, and that's not shown here as well. So when you go down to this part here, so we compute these things, and then these are the w to power n. So n is now 0, 1, 2, 3, and these are the W to power 3n, n equal to 0, 1, 2, 3. So n is 1, cube 6 9th. Okay, and then once these are multiplied, then you compute. What do you compute after these? So these are going to be n is 16. So these are n by 4 point DFTs, and what's pasted here? These are the 4 point DFTs that I just showed in the very beginning. So just take that and put it here, and so that's kind of your last homework problem. Okay, so I'm not going to give you that page, but of course you can download these things from the internet. It doesn't matter, but still try to do that. Okay, so any question about split radix FFT? Yeah.
What are the advantages of this as compared to other?
Excellent question. What are the advantages and why are people interested in these things? Ultimately, the advantage is savings in these twiddle multiplications. So people have been, of course, the Cooley-Took algorithm is a great algorithm. It has n log n complexity, but the split radix FFT reduces the number of multiplications some more. You can look at the tables, how much it reduces. Not that much, but yes, it does reduce to a great extent for a very large n. So there has been interest in these kinds of things. Sometimes you will see in the internet or wherever you want, sometimes you will see that the split radix is described by what is known as an L-shaped butterfly. And if you look at these kinds of things here, so that's kind of one L butterfly, and that's kind of another L butterfly, and that whole thing here is let's see, here goes here and comes all the way. That's kind of another L. So I don't think we need to worry that much about all these things. But people do say that the split radix is composed of these L-shaped butterflies. So we don't need to worry very much about that. Okay, so I think with that, any other questions? Yeah.
How do we perform the complex computation in hardware?
Aha. Yes. Yeah, I mean, yeah. So I'm not going to go into that very much. Okay, let's just talk about, okay, what exactly, I mean, I can just talk about what exactly is, how does the hardware compute, okay, the complex numbers. So let's say that I have A multiplication A plus JB times C plus JD, which is AC minus BD plus J times AD plus BC. Okay, so how does the hardware really compute? So the hardware, you have to keep track of which wires are imaginary and which are real on your own. And so there is, yeah, so the hardware is not remembering which is complex and which is imaginary. So it will compute these things. It will compute A times C. So if we have A, B, C, D as the 4 inputs to some box, it's going to compute AC minus BD and AD plus BC. So yeah, we have to keep track of that in the hardware and make sure that all the imaginaries are added to imaginaries and real to real. When we multiply by J or minus J, these are swapped and negated if need be. So we have to do those things on our own. And ultimately, how do those things map into hardware? Yes, the class I will teach next year, 5329, that goes into a lot of detail about hardware implementations of these in RTL code, and students spend many weeks. And so, yeah, I see that a number of you took the class last spring. Those of you who will be here next year and are interested in RTL code design and Verilog code design, you can take that class as well. Okay, that's good. Any other questions? Okay, let us jump quickly to the next topic that I want to talk about, which is the composite FFT. Okay, so what is the main idea? By the way, what I would say, this is another block diagram that I just grabbed. What I would say before you start your next homework, I would say just sit down. Just because I didn't ask you doesn't mean anything. Just sit down and draw the 16-point decimation in time and decimation in frequency complete diagram on your own before starting the homework. That will help you a lot. Okay, so now let's talk about composite FFT. So before I get into the formal description of that, let's start with an example of n is equal to 15-point FFT described as the product of 3 times 5 or 5 times 3. It does matter how you decompose, but let's say 5 times 3. So in general, P times Q. So we will talk about the derivation and see what that means. But basically this is what it is. So if we have 15-point DFT and I want to describe that using 5-point DFTs and 3-point DFTs, okay? So here is the solution. Let's start with the solution and then we'll get through the derivation later on. So I can describe that by using 3 5-point DFT on the left side, 3 5-point DFTs. On the right side, 5 3-point DFTs. Okay, so a composite FFT of length P times Q will have Q P point DFTs on the left and P Q point DFTs on the right. Okay, so how do we connect these things? So the inputs here are going to be 5 samples, 5 point. So the first input is going to be 0, 3, 6, 9, 12. Next one is one more than these things, 1, 4, 7, 10, 13. And then one more, 1 plus 1, 2, 5, 8, 11, 14. So that's going to be the input pattern. The 5 outputs coming out of these, okay, so the first of second, first of third will go here, second from everywhere will come here, third from everywhere will come to the third, fourth from every all these 3 will come here, and the last from all these 3 will come here. So that's the 3-point DFTs. Okay. These multiplications will all be 1. So there's nothing to do with the first one, and these top ones will also be 1. Okay. So now what happens? The twiddles, so-called twiddles, are going to be W squared, W cubed, W to the power 4, and these are going to be W squared, W to power 4, W to power 6, W to power 8. Okay, so those are going to be the so-called twiddle factors, and then when we finally compute this is going to be x0, x5, x10, x1, 5 plus 1, 6, 10 plus 1, 11, 1 plus 1, 2, 6 plus 1, 7, 11 plus 1, 12, 3 plus 5, 8, plus 5, 13, 4 plus 5, 9, plus 5, 14. That's the pattern. Okay, I've given you the solution. It's good to know what the solution is, and its solution is really simple. It's not that involved. If we are decomposing 5 times 3, we have 5-point DFTs, 3 of them on the left, 3-point DFTs, 5 of them on the right. These are the total factors. And the input sample numbers are here, the output sample numbers are here. Okay. I don't think that looks that bad. So now let's try to see how to derive this structure. So xk is equal to summed over n equal to 0 to n minus 1 xn e to the power minus j twice pi over n kn, and this can be written as n equal to 0 to n by 3 minus 1, because I'm describing these as n by 3 points, so that's really n by 3. Okay, and then okay, so as you can see here, the sample index n matches this index n, and this is x0, 3, 6, etc. So which are here 0, 3, 6, etc. And then the next one 1, 4, 1, 4, etc. And the next one 2, 2 plus 3, 5, 5 plus 3, 8, etc. So these are the n by 3 points. So, so now if I multiply this 1 out, multiply this 1 and write that here as e to the power minus j 2 pi over n times k. So that's w to power k, multiply these two and then take it outside the sum, that becomes w to power 2k. Okay. So now this is equal to, so you will quickly recognize that this thing is the DFT of x3n, DFT of x3n plus 1, x3n plus 2, and that's really what we see here. These are the DFTs of the x3n. This is x3n. I can call this 5 samples as x3n. And these are x3n plus 1. And these are x3n plus 2. Okay, so if I call these as P, Q, and R, if I call this Pk is the DFT of x3n, Qk is the DFT of x3k plus 1, and Rk is the DFT of x3n plus 2, Then these things here are computing P, Q, and R. So you can think of this as P0, P1 up to P4, Q0, Q1 up to Q4, etc. Okay, so this becomes equal to Pk plus W to power k Qk plus W to power 2k Rk for k equal to 0, 1, 2, 3, and 4, because because this is only defined, these are only defined. This P, Q, and R are 5-point DFTs, and they're really defined for k equal to 0, 1, 2, 3, 4. It's not that I don't know what happens if k is, for example, 15, but that same thing as P0. P15 is same as P0, P16 is same as P1, but what will change are these W parameters. So just like the decimation in time FFT, if I need to compute, so how do I compute? To compute x, so this will help me compute x0 through x4. Then to compute xn by 3 to 2n by 3 minus 1, use x k plus xk plus n by 3, which would be k equal to again 0, 1, 2, 3, 4. So 0 plus 5. So this is going to be p k n plus n by 3, which is same as pk, plus w to power k plus n by 3 q k plus n by 3, plus w to power 2 times k plus n by 3 q k plus n by 3. Okay, so these things don't really matter. This is same as pk, qk, this is rk, and this is rk same as k plus n by 3. Okay, so but let's take a quick look at these quantities here. W to the power k plus n by 3, W to the power okay, yeah, that's fine. Okay, so W to power k plus n by 3 is e to the power minus j 2 pi by n k times e to the power minus j 2 pi by n times n by 3. So that thing is equal to same thing as W to power k times, all I want to show you is that this quantity is e to the power minus j 2 pi by 3. So this is equal to pk plus e to the power minus j 2 pi by 3 times w to power k qk plus 2n by 3, w to the power 2n by 3, multiply this by 2, 2n by 3 will be 4 pi by 3, e to the power minus j 4 pi by 3, w to power 2k rk. And to compute 2n by 3 to n minus 1, I can just say x k plus 2n by 3 is going to be, and I can skip a couple of steps, so this will be p k plus 2n by 3, which is same as pk, w to the power k plus 2n by 3 will be w to power k plus 2n by 3 will be same as e to the power minus j 4 pi by 3. So this 2 is same as that 2 we saw here, e to the power minus j 4 pi by 3 times w to power k qk plus e to the power minus j 8 pi by 3 W to power 2k Rk. Okay, so remember we had that other equation here as well, Pk xk was Pk plus W to power k Qk plus W to power 2k Rk. Okay, so now I am going to write down these three equations in terms of a matrix. So if I write down these equations, okay, what was xk? Xk was Pk plus this plus that, 1, 1, 1. What about xk plus n by 3 was Pk plus this quantity times that plus this quantity. So 1 e to the power minus j2 pi by 3 e to the power minus j4 pi by 3 and 1 e to the power minus j4 pi by 3 e to power minus j pi by 3. Does anybody have a clue about what that matrix might be? Any volunteers? Some of you took my 45-41 class. We have seen this before in that class. Okay, remember that DFT matrix? 1, 1, 1, 1, 1, 1, 1, W, W squared, W cube like that, W squared, W to power 4, all those things. So if you take the 3 by 3 3-point DFT matrix, then W is e to the power minus j2 pi by 3. And that is the DFT matrix for 3-point DFT. So what we are finally understanding are these three things are the 3-point DFT of those three things. Okay, so what does that tell us? So if we took this Pk, so I take P0, so this first one, so if I just take k equal to 0. So in this equation, substitute k equal to 0, k equal to 0 means W to power 0, 1, W to power 2, 0 is 1, PQR, so P0, so P0, Q0, R0, 3-point DFT of that will be K0, X0, X5, X10. So that's what we see here. Okay, so if I substitute k equal to 0, then that's what is k equal to 0 here. If I take k equal to 1, the twiddle has to be W to power 1 for Q, that's W, W to power 2 for R. So these twiddles, they come here, 3-point DFT, we get X1, 1 plus 5, 1 plus 10. Okay, k equal to 2, twiddles are W squared multiplied to Q2, W to power 4 multiplied to R2, all the second things come here, third things W cube, W to power 6, 4 and 8, and we get all of these. So you can think of that, this is k equal to 2, k equal to 3 and 4. So this is kind of a one simple example, but at least are you now convinced that this is the, say for this simple example we are able to compute the 15-point DFT using 5 3-point and 3 5-point. Any questions about this? So let me try to prove this to you using a more little more complex mathematical formalism, and so we will go through the same thing, but using a little more mathematical formalism. Okay. So now N is equal to P times Q, and I can describe. So xk is summed over all n xn e to the power minus j2 pi over nkn. So let's see, let's divide this n. Okay, so think about this. So how is this n divided? So this n is divided into 0, 0, q. So p times q, q is 3. 0, q, 2q, 3q, 4q. 4 is 5 minus 1. So these first group of samples are going to be, so if I just call this n, think about n is written as qt1 plus t2. Okay, so q times t1 plus t2, so this will be, so q goes from 0 to p minus 1. So for this one I can say t2 is 0, t2 is 0, and these inputs are x qt1, xqt1. Okay, so we are going to write this as, so first of all we will take this x qt1 plus t2 and compute, we are computing what? P point DFTs. P point DFTs. So e to the power minus j 2 pi over n, n is now going to be p, the length will be p point DFTs. Okay, so n is replaced by this quantity, and it may not be obvious yet, but so let's define k as another index k1 plus p times k2, and this k1 will be 0 to p minus 1, k2 will be 0 to q minus 1. Okay, so let's take a quick look at that quantity here. So e to the power minus j 2 pi over n, k replaced by k1 plus pk2, n replaced by q t1 plus t2 is going to be e to the power minus j 2 pi over n, k1 qt1 e to the power minus j 2 pi over n, k1 t2 e to the power minus j 2 pi over n, p q k2 t1 times e to the power minus j 2 pi over n, p k2 t2. Okay, so we have these many things here. So this PQ is same as n, and the n and n cancels out, and this is even 2 pi, some number times even 2 pi. So that whole thing is 1. So we don't need to worry about that. Okay, so n is p times q, so here q cancels out, so we are left with p, and this is P times Q. The P cancels out, we are left with Q. And why does that matter? Because it matters if we are taking P point or Q point DFTs. So now I can group this one here, e to power minus j 2 pi by P times K1 T1 summed over T1 equal to 0 to P minus 1. Okay, so so T1 goes 0 to P minus 1, T2 goes 0 to Q minus 1. So, okay, so now, so that's, these things are going to be P point DFTs and how many? T2, because this will be, eventually I will get to the outer sum. But so now these whole things are multiplied by these twiddles. So those twiddles are this quantity here. So this thing, so let me just write that as W to power K1 T2. So that is W to power K1 T2 is here. Okay. So once we multiply by twiddle factors, then let's put this in a bracket. Then we take the outer sum, summed from T equal to 0 to Q minus 1 times that thing here, e to the power minus j 2 pi by Q times K to T2. K to T2. Okay, so that's the more mathematically formal way of describing the decomposition of P times Q point using, these are Q P point DFTs multiplied by the twiddles, and then P Q point DFTs, there will be P of these. Okay, so that's so finally we will get the final result K1 plus P times K2. So I can describe this by a diagram, by an equivalent diagram like the one I had shown before. So we have Q P point DFTs, and then there will be these twiddles. So these are all ones. This will be W, and the next one will be W squared. I'm not going to write this a lot. This will be, this quantity, however, will be W to power P minus 1. Okay, so then these will connect to compute X P times K2. Okay, where K2, index of K2 goes from 0 to Q minus 1. So this will be 0. When K2 is 1, this will be P, 2P, etc. And then finally, we will compute X P times K2 plus P minus 1. These are going to be Q point. So So this equation here, QP points followed by twiddles times P Q point. Okay, so this is P, because this is this one is K1 equal to 0 and K1 equal to P minus 1. So the index K is described by the double index K1, K2. The index N is described by the double index T1, T2. So we divide N into T1, T2. So the time index N is mapped to a two-dimensional index T1, T2. The space index, frequency index K is mapped into a two-dimensional index K1, K2. Okay. So I think that's sufficient description for you to start your homework. There is more that we can continue. Let me take a very quick look and see if we can walk through some of the homeworks and see what I have asked you to do. So in one homework problem, I've asked you to show that the DIF can be obtained from DIT by twiddle shifting. Okay, so that's the DIT. So this is in your handout in the Canvas page. And if you redraw this so that the 0 is followed by 1, followed by 2, and that's what is in the next diagram. And that's the redrawn diagram. So the 0, 4. So these are this is the same equivalent diagram, because ultimately we want to show the equivalent to DIF, which means the inputs are in the right order, outputs are in decimated order. And the DIF output, DIF. So how do I show that this thing here, these are 0, 1, 2, 3. How do I show these are equivalent to that? I need to get 0, 1, 2, 3 here, then they will be equivalent. So instead of pushing twiddles to the right, you push them to the left. So if you push W to power 1 from this butterfly here to the left, so that's W to power 1, and that 2 becomes 2 plus 1, 3, and that disappears in this 3. We shifted 1 back, that becomes W squared, and that's exactly what we have here. So anyway, that's your homework. I don't want to say anymore. I already solved it for you, but you have to still write it down. Let me see where the homework problems are. There is quite a bit of drawing to do. So the 3-point DFT equations we went through last class. You trace this and show that these are indeed satisfying that equation that we talked about, and even I talked about today. This one is a little cumbersome, so it's a 5-point. You can think of that as a radix 5 butterfly, if you like. And same here, radix 3 butterfly. It's a bit of arithmetic. I feel bad about it. I feel bad to give you this problem. It can take some time, but it may be a good practice. And I'm not teaching Winograd FFT, but that would be the 5-point Winograd FFT. Okay, so transpose this structure. So that's just transpose this, put these things back to get another equivalent 3-point DFT. That's number 2. Number 3, I just solved how to show the equivalence between DIT and DIF by twiddle shifting. Number 4 is asking you to do 16-point split radix, and then by twiddle shifting of the 16-point DIT, so the equivalence of the split radix and the DIT. Problem 5 is composite FFT. So it's showing how to design 1024-point FFT using this 32 times 32 and 256 times 4. So you will have 4 256 points on the left and 256 4 points on the right. And this is, well, this bracket is here. That means this 8-point and 4-point are used to compute 32-point. And then this 32-point is same as before. So there is 3-stage decomposition, or I might say 2 stages. And the last problem is how to implement correlator using FFT, 8-point FFT. So we have a 4-point sequence 0, 1, 2, 3, input. Second input y0, y1, y2, y3. We want to compute the correlation 7-point Zn using DFT. So when I compute, so this can be computed by Xn and then append 4 zeros, right? So you append 4 zeros, and so you will show where to append those things. So you get 8 quantities, and then that 8 goes to 8-point FFT, and then y same way with the 0 and goes to the merge goes to 8-point FFT, and then you multiply these two, and then take the 8-point IFFT, and then you get 8 values. And so draw this 8-point using decimation in time, and same here decimation in time. This one, the IFFT is decimation in frequency, so take the decimation in frequency, conjugate the twiddle factors, have the scale 1 by n. But here I want to see if you line them up, where is 0, 1, 2, 3, where are the zeros, how they're appended, where they're placed. If you don't do that right, it won't be computing the right things. And then finally, when you are computing the 8-point IFFT, we really need 7 values. So somehow or other you can see that the last IDFT will be 0, and so I've asked why is the last IDFT coming out of here, the 8th one, not necessary, because that can be proven to be 0. Okay, that should keep you busy. This is a long homework, so please do get started and do not wait until last couple of days. Okay, so we will stop here. I am happy to stay 5 minutes or so. You can ask me any questions, quick questions if you like. Okay, please tell me your homeworks.